Hello guys, this is Shishir C from first time from Chevrolet section, roll number 23 CS 1535. Today we are going to study mathematics. Index Taylor theorem for the function of variables, Jacobian matrix and determinants. Next index error and approximation, larger method of undetermined multiples. Taylor's theorem for functions of variables. Taylor's theorem for function of variables statement: if f of xy has continuous practical derivatives up to nth order in a neighborhood of a point AB, then f of a plus h bhk is equal to f of ab plus h dou, dou by dou x plus dou y. F of ab plus 1 by 2 1 by mod 2 bracket h dou by dou x plus k by dou y whole square f of a comma b, and then continues for the nth order, where Rn is equal to 1 by uh, nth factorial h dou by dou x plus k dou by dou y whole power n. This is how we have to write. And then this is called the Taylor's theorem of xy about the point a comma b. If a is 0 and b is 0, we get Marconian's form of Taylor's theorem. Expand ax by ex by by using Mercurius theorem upon the third term. Solution. This is a problem. Solution. Since the expansion required the power of x comma y, the point a comma b associated with the 0 comma 0 and expression of f of xy about 0 comma 0 is given. F of xy is equal to f of 0 comma 0 plus x f of x is equal f of x into 0 comma 0 plus f of y comma y into 0 comma 0 plus 1 by 2 factorial of x square fx into 0 comma 0 plus 2xy, and then continues till 3xy. The function and its parallel derivatives adequate at 0 comma 0 is as follows. Substitute this value in the expansion of x comma y. We get f of x comma y is equal to 1 plus ax plus by plus ax plus by whole square, and then continues. Maximum and minima of function of two variables. Maximum value of function. A function of f of x is said to have maximum point a comma b if these exist a neighborhood n of a comma b such that f of x y is greater than f of ab for all x comma y into the natural numbers. Minimum value of functions. A function f of x y is said to have a minimum point a comma b if this exists a neighborhood n of a comma b such that f of x minus y is greater than f of a comma b for all x comma y nth number. The necessary condition for functions of f x to have either maximum and minimum at a point a comma b are functions of a comma b is equal to 0, or f of y a comma b is equal to 0. The point x y where x and y satisfies f of x comma y that is equal to 0 and f comma y that is equal to 0 are called as stationary and critical value of the function. Suppose a comma b is critical value of the function f of x y, then f of x a a comma b is equal to 0 point it is equal to 0 and y ab is equal to 0 as given here. Then the functions f x comma y has maximum at a comma b if ac minus b square is greater than 0 and a is greater than 0. The functions of x comma y has minimum at next one, the minimum at a comma b if ac minus bc is greater than 0 and a is greater than 0. Working rule: find x comma y, y comma f comma x, f comma y, solve the equation, then find this is how it follows. Next, Jacobian matrix. This make a list of these. Let's go to Jacobian matrix and determinants. In vector calculus, the Jacobian matrix of vector valued function of several variables is a matrix of all first order. Then when this matrix is square, um, when the matrix is square, the function takes in the same number of variables input, number of vector components out, determinant referring to the Jacobian board matrix. Determinants are often referred to simple Jacobian lecture. Suppose Rn is proportional to Rm is a function, then each first order parallel derivatives exist. N Rn, this function takes place x over Rn whole. Um, as input produces the vector f of x is corresponding to Rm as output. Then the Jacobian matrix F is defined as matrix n into n denoted by J, as it follows like this. Errors and approximation. Maybe this is the last concept for us now. Yeah, we can use differential to calculate small changes in the department variables of a function corresponding to small changes in independent variable. This theory behind it is quite simple. Form of chapter differential differentiation. We know that limit of x comma 0 um, y by x y by x is equal to dou y by dou x. For small x, we can therefore approximate small y as f of x and into x. This is all there it is to it. This is all there to it. Suppose we have to calculate 4.01 square. We let y is equal to x square into x naught is equal to 4. Y naught is equal to 169. This is how it follows. Summary and rationale. The basic idea is to convert a concentrate problem into a function into a form such that the derivatives test of unconsidered problems can still be applied. The relationship between generated of the function and gradient of the consideration rather naturally leads to a reformation of original problem known as the uh, Lagrangian function. In general case, the function is defined as L f of L into x lambda corresponding to f of x plus lambda gx. Lagrange, where f of x comma g of x lambda is called as Lagrange multiplier. The method can be summarized as follows in the order of minimum and maximum function f of x. Substitute the equal constraint g of x is equal to 0. Find the stationary point of L. Consider as a function of x and larger multiple lambda. This means that all partial derivatives should be 0, including the partial derivatives with respect to lambda. Dou L by dou x is equal to 0 and dou L by dou lambda is equal to 0. Dou f of x, dou x plus lambda into dou g of x, dou x is equal to 0 and g of x is equal to 0. The solution corresponding to original considered optimization is always a saddle point of Lagrange function, which can be identified among the stationary points from the difference of border Hassan matrix. The following is known as Lagrange multiple theorem. Let Rn be R be the objective function where g function Rn Rn to Rc be the constant function both belonging to C1, that is having continuous first derivative. Let x be an optimal solution to the following optimization problem such that for matrix of partial derivatives g into dx jk is equal to dou gi dou gj by dou k xk rank dg into x that is equal to c greater than n maximize f of x subjected to g of x is equal to 0. Then there exists a unique large number lambda such that d of x is equal to lambda t. Note that this is somewhat conventional. The larger multiple theorem states that maximum or minimum of the function evaluated under the equal constraint qualify applies explained below. Then the gradient of the function at that point can be expressed as a linear combination of the gradient of the constraint at that point with a larger multiplier acting on a coefficient. This is equivalent to say that any direction perpendicular to all the gradient of constraint is also perpendicular to the gradient of function, or still saying that the directional derivatives of function is 0 is every feasible direction. Thank you so much. Thank you for watching my video. Bye.